I'm so excited to have our session today. We have Alan Fritz with us. Alan is our K-State wheat breeder in Manhattan. Alan has tons of experience out here in Northwest Kansas because he's from right across the border up in Nebraska. So he has lots of experience with wheat production in our area. And I actually spent quite a bit of time on the phone with him the other day because I'm looking at wheat. I had questions and I thought, who better to go to with someone who with lots more experience than I've got on wheat. And actually, I took breeding class from Alan when I was in grad school. So I have a special place in my heart for understanding wheat and its production. And so I asked Alan when we were on the phone talking about this, I said, hey, can you talk about what's going on out in the field? And then let's go ahead and have some other discussion about the breeding efforts for Mosaic virus, because we've had lots of challenges with wheat streak mosaic and triticum and high plains mosaic. So I asked Alan if he would kind of give us an update of what's going on in our K-State wheat breeding program. So with that, I will stop sharing. Alan, you can share your slides and we will
Right.
be ready to roll here.
Sounds good. Um, all right. Hopefully everybody can see the screen there. So thank you,
Yes, it's
Jeannie.
good to go.
I'll probably start just kind of talking a little bit about vernalization because some of the first questions like, hey, when is wheat vernalized? And what happens when it's fully vernalized and all that. So we'll just walk through it. So vernalization was defined by Chouard in 1960. It's the acquisition or acceleration of the ability to flower by a chilling treatment. So there's a difference between winter wheat and spring wheat, as winter wheat requires a period of cold in order for the plant to convert from a vegetative state to a reproductive state. Um, so when does vernalization start? Vernalization begins as soon as the seed can begin as soon as the seed imbibes, assuming it has temperatures that are conducive to vernalization. And so we don't have to wait until the plant's emerged. As soon as that seed's imbibed, vernalization begins. Um, I just looking through the literature, I was a little surprised. I guess there's things that I thought I knew, but just looking through the literature, the understanding of the temperature threshold and the optimum temperature has been a bit of a journey, and there is some conflicting information in the literature over a fairly significant period of time. But we can give you some of the better information here. Brooking in 1996 had shown a rate of vernalization increases from 1 degree C to 11 C in a linear fashion. Rate of vernalization decreases at temperatures above 11 C and doesn't occur at 18 C or above. That was kind of the information we worked off of for a while, and I think that's kind of what I knew in graduate school. Um, Probably a more accurate assessment was done by Porter and Gowith and that was reported in 1999. So they reported minimum, optimum, and maximum temperatures for vernalization. So they have a minimum of minus 1.3 C, so a little bit below freezing. Our maximum or our optimum is 4.9. And the maximum is 15.7. So what that means is that 4.9 C, that plant's going to vernalize as efficiently as possible. So that's if you were going to say, how do I find the vernalization period? You would want to use that optimum temperature because that's going to be the minimal amount of time that you would need to get vernalized. And so that's our vernalizing temperatures. Um, so part of the challenge in terms of like one of the questions Jeannie asked me when we were on the phone is like, are we vernalized? I'm like, well, I mean, part of that going back to that slide is we don't have a constant 4.9 degree C temperature in the field. We have our diurnal variation, we have our daily variation. So there is a piece there where that's not so straightforward of saying, hey, this has a 5 week vernalization period. That's 5 weeks at that optimum temperature. It would take longer at suboptimal temperatures. So as you go lower than or higher than, that vernalization requirement is not going to be saturated as efficiently or as quickly. As far as the genetics behind it, there are 4 genes that control vernalization in wheat. Wheat is a hexaploid. It's a combination of 3 different grass species. We get a vernalization gene from each of those 3, plus we have another vernalization gene on chromosome B, 3B. Um, as far as how that works, winter wheats have recessive alleles at all 4 loci. So spring wheats have at least one dominant vernal allele. So it doesn't take all four genes being spring for it to be spring wheat, but we have to have all four genes being recessive in order for us to be a winter wheat. Um, if you're really interested in diving into the mechanisms of vernalization, it's an interesting kind of biological mechanism that is really kind of a clock mechanism that controls gene expression that triggers the flowering mechanism. So if you really want to dig into that, the Lukanov paper is a pretty good one for that. As far as duration of vernalization, allelic variation of the recessive vernal alleles leads to differences in vernalization requirement and heading date. So what does that mean? Probably the simplest example would be Yan et al. In 2015. They were looking at Jagger in 2174, and they both have a recessive vernalization locus, but it's a different allele, so a different form of the gene. And Jagger has a shorter vernalization, so it shortens the vernalization requirement relative to 2174. So it's not just it's a switch that's on or off. There are different alleles that control how long that vernalization period is in a given variety. So the vernalization range for varieties is generally from 2 to 7 weeks. Again, that would be if you're using that optimum temperature. David Worrell, who was the breeder at A&M and then the Syngenta breeder at Vernon, used to say that Overly, which is a variety we released early on in my time at K-State, if all you had to do was wave an ice cube over it and it was vernalized. That's not quite true. It does have a couple of week vernalization, but it's a really short vernalization period. And then that vernalization requirement is met. And so, as far as needing additional vernalization to flower, it doesn't need that. That doesn't mean as soon as that vernalization requirement is met, it's going to take off. Uh, but it does mean that that vernalization requirement has been saturated. The flowering date then is influenced by vernalization requirement and photoperiod, as well as the temperature regime that we get in the spring. So photo a lot. We talk about photoperiod as if varieties are either photoperiod sensitive or photoperiod insensitive, and they do tend to fall to those categories. But there's a range of responses to photoperiod. So there are some things that are really strongly responsive to photoperiod. An example of that that's been out in the variety mix in recent years would be LCS Chrome. So it is a very strongly a photoperiod sensitive variety. And so even though its vernalization requirement might be met, it's not going to flower until it's had the photoperiod signal to convert to flowering. And so what that means is for something like Chrome is it's probably going to flower for us here in Manhattan, it's going to flower about May 8th every single year because it's really going off that light signal. So its heading date doesn't really float around depending on the temperature signal. It's really more determined by the light signal that it's getting. Whereas most of our other varieties aren't entirely photoperiod insensitive, but they're mostly insensitive. So they're going to respond much more to temperature signals. And some of that allelic variation at the vernalization genes, there's some earliness per se genes. All of those genes kind of come together to give every variety sort of its specific pattern for how it's going to respond and how it's going to take off in the spring. So that's why we see differences in heading date. That's why we see things hit first hollow stem faster or take longer or hit it faster. Um, Interestingly, you can devernalize wheat. Um, Temperatures above 35 degrees, particularly as a shock, if you go directly from vernalizing temperatures to high temperatures, it can reverse the vernalization process. I don't think that was first described in rye in 1948. There's a molecular analysis of that that's published. Um, for the most part, I don't think that this is a real issue for producers. We see it in the breeding program. We even saw it last fall in our crossing block greenhouse. We took plants out of the vernalization chamber. We took them to the greenhouse. It happened to be a really warm day. We should have just left them at somewhere at 60, 70 degrees for a couple of days. But we lost some of the vernalization in some of those materials. We don't
Alan?
normally see, yeah,
When you say 35, you mean 35 degrees Celsius, correct?
yes,
Okay,
yeah.
so what does that convert to Fahrenheit?
Oh gosh, that's
Sorry, I could have done that really quick.
Yeah, I'm terrible at that conversion.
95,
90, yeah,
95.
that's a really high temperature. And I think we lose that vernalization. We can devernalize, I think, at somewhat lower temperatures. That's what's reported in the literature. I don't think we see that in field situations. One is we don't normally get that. I mean, we've been warm, but we haven't been 95 degrees warm. I think the other part of that is that loss of vernalization depends on the saturation of the vernalization response. So once something is really fully vernalized, it's harder for it to be devernalized. We'll mostly see devernalization if we're not quite fully vernalized. And so again, it's not necessarily a thing where it's a switch that's either on or off. As we increase the time of vernalization, if you pulled the things out at 2 weeks, at 3 weeks, at 4 weeks, at 5 weeks, at 6 weeks, and 7 weeks, they're all eventually going to flower. It's just how long does it take them to go to flowering? And so once we've saturated that vernalization response, we're much less likely to devernalize. So I don't, it's more of an oddity, but I don't think we really see that under field conditions. As far as cold hardening, Roberts described cold hardening in wheat. Duration of hardening was more important than the stage of resistance. And so some of this is going to be happening for us in the fall. And how do we achieve our cold tolerance? And so when that wheat first emerges, we don't have a lot of cold tolerance to it. But over the first 10, 11 days, if we have cooler temperatures, we're going to start to cold harden that plant so that it can tolerate increasingly cold temperatures. And so and as we have more of those temperatures, then that plant is more tolerant of a cold period. And so I think the clearest example of when we had an issue with this was probably the fall of 2014. We were really, really warm. In fact, I think we were in the upper 80s, and about 11 hours later, we were at 7. And we killed some varieties we basically killed. And that was because they'd really been so warm that we'd lost the cold hardening in some of those varieties, and they just really got hammered in that cold situation. So everybody kind of remembers 2015 as a year with a lot of winter kill, but that winter kill actually happened on, I think that was like November 11th, when that 85 to 7 event happened. One of the things that's important, particularly as we talk about the crop that we have in the field right now, is I think the concern is, hey, if we've already saturated our vernalization, are we really at risk for increased cold injury? One of the positives is that maximum hardening persists in wheat for several weeks past the saturation or completion of vernalization. So this isn't a case of where once you're vernalized, you start to lose cold hardiness. That's not true. That cold tolerance persists. Um, but the literature also says, and there's evidence that wheat in the field has less cold resistance late in winter than in autumn. So once we've cold hardened, we do start to lose that a little bit. And so we start to have less cold tolerance. As it pertains to the crop in the field right now, I'm not terribly concerned. If we were to go to 20 below, yeah, I'd probably be concerned. But as long as we don't do something like that, and even when we had Providence on increase, I think it was the 26th of February. We went to like 23 or 24 below, and I was really, really concerned because Providence has a lot of spring wheat in its background, but we were fine. So I think that we maintain that cold hardiness, that cold tolerance for quite a while after vernalization is satisfied. Um, so this is the first question that I had. So this was precipitated a little bit by some of the questions about um, having wheat with more growth on it than we would expect. And so this is just a question about how much of the wheat in your area would you consider to be excessively growthy? And I'll leave it to you to define excessively growthy. Um, but less than 10, 10 to 25, 25 to 50, or greater than 50% are the options that I gave you. I didn't figure in any area we were probably more than 50% based on windshield survey, but anyway, those were the categories I gave you. So uh,
Okay, guys, we'll give you about 5 more seconds to get your answers in here. Looks like we've got about 70% of the folks who are joining on Zoom have responded back. If you're joining on YouTube, you can put that in the comment section or the chat section on YouTube. So with that, we'll wait just a couple more seconds here, and then we'll go ahead and end the poll. Okay, here are the results. So less than 10%, we have about 35% of our attendees are saying that, clear up to a little bit of a curve here, up to 25% said they're greater than 50% of their wheat seems to be excessively growthy.
Yeah, all right. So quite a bit. I don't necessarily find that completely shocking, just from the standpoint of we had a really warm fall. I think we did have some folks who planted a little bit early, but I think even some of the discussion prior to starting here was just we had a warm fall, so even things that were planted normal time or even slightly later just had more growing degree days, more opportunity to put on biomass in the fall. So I guess I'm not terribly shocked by that, but it is a little bit of a concern that we're that growthy. What are the concerns? And so I guess I don't know if this was the appropriate place to insert the picture. So we had a conversation earlier about before we jumped on the webinar. Are there any pictures to kind of show what we're looking for? Like, if things look like they're dead? I would say probably my first response is you're not necessarily going to go out and do anything about that crop right now. So your best bet is to wait a couple, 3 weeks, and it's going to be really clear because things are going to really start to green up, and you'll see whether things are fine or not. This is a picture from A&M from a few years ago when they had some freeze damage, and you can see the leaf tissue up above the thumb there. It's all pretty brown, and that wheat doesn't look very happy. But there's still the growing point that's still green. So that plant's still okay. That head's still okay. Obviously, stage wise, this is right at first hollow stem. We're starting to push the growing point above the ground. I don't think we're probably there in most of our places yet. Maybe on the southern border, we're starting to get where we might need to start looking for that. But that growing point is still okay. So the plant can look really awful and it can still be okay. And it'll still put out leaves. It'll still be fine. A lot of that growth that's on there isn't going to hurt you if it's gone. But so anyway, that was the picture from A&M. I think kind of some take home points. True winter kill is usually from cold soil temperatures. And we usually see that when we have drier soils. And normally what we would talk about there is we need to have soil temperatures below 10 degrees Fahrenheit at the crown in order to really be at significant risk for true winter kill over the winter. I don't think we're really anywhere near that. I think our risks are a little bit different in this crop. Wheat that's lost its cold hardening only recovers about 39% of the freezing tolerance after reacclimation. And so what they did in this particular study is they had taken wheat, they had it start to grow, lost its cold hardiness, then give it reacclimation temperatures. Canola would go back to pretty much 100% of its cold acclimation. Wheat does not do that. It only goes back to about 40%. And that's why I would say we're probably in that curve where we're losing that cold acclimation right now. So if we were to go to really cold temperatures right now, I think there'd be some risk. So if we would go to well below zero, I think we'd have some risk, but otherwise I don't think we're in a real serious situation yet from that. The other point that I kind of need to make is vernalization is not tightly associated with degree of cold hardiness. So sometimes we think about, well, it has a long vernalization period, so it's going to be more cold hardy. That's actually not really true. Cold hardiness and vernalization are correlated, but it's not a really tight association. So I was just thinking some questions that I might get. And so I anticipated those, and so we'll take a shot at those. And if there's others, that's also fine. Have we lost some cold tolerance? That's hard to answer definitively, but we do know that the wheat plant will maintain its cold tolerance past the saturation of vernalization. That's encouraging, but we also are probably at that point where we're starting to expect to lose some of that cold tolerance as we head into jointing. And so I would guess that right now we're probably not as cold tolerant as we were a month ago, but I don't think we're at a point where we're really, really susceptible to kind of what I would call normal cold temperatures for this time of year. Will all varieties react similarly? Similarly, no. You're likely to see a bunch of different responses from varieties. We see this every year in the breeding program. There's things that get burned back quite a bit. There's things that don't get burned back. Usually, we're discarding those things that suffer a bunch of burn back, but they don't necessarily yield poorly. Sometimes those things actually end up yielding really well. That cosmetic damage is just that. It's cosmetic. What makes it really hard to be able to tell you about any particular variety or to generalize is that there's an interaction with vernalization, temperature, and photoperiod for the breaking of dormancy. So at this point, you could go dig plants up out of the field, bring them in, put them in a greenhouse. They're going to take off. So our vernalization requirement is almost certainly satisfied on everything right now. Photoperiod will be a factor. So things that are more strongly photoperiod sensitive are going to be holding on to their dormancy, while those that are more photoperiod insensitive can be starting to break that. Once we have all those triggers, then we're responding to temperature. And if we go back to things like Jagger, which was on a lot of acres for a long time, it could get ahead of itself because it was responding to temperature. Short vernalization, photoperiod insensitive, gets a period of warm temperatures in the spring, and it goes, oh, it's time to go. It's time to wake up from my slumber and get going and put a head up. And so every variety is going to respond a little bit differently. Typically, things that are earlier maturing are going to be ones that respond that are more photoperiod insensitive and respond more to that temperature signal. Does burn back equal yield loss? No. I mean, there could be some really ugly wheat out there, and that does not mean that we've lost yield. Loss of tillers will result in yield loss. So we need to watch that first hollow stem and look for that. But if we see that when we get the first hollow stem and we can find that growing point, that tiller's fine, and we're not really losing anything at that point. We're just burning off some of that excess for biomass that we've put on there. So I would say, I mean, I drove by our plots out at Rocky Ford Research Farm yesterday. There were some things that were planted really early for barley yellow dwarf exposure, and they look bad. They're very burned back. They look very brown from the road, and everything else looks nice and green. And I think if you were just doing a windshield survey, you'd go, yeah, that big wheat really looks like it's in trouble. It's not. It's not digging down in the canopy. Everything's okay. It's just been burned back. There is a threat though. The big wheat has already used and it will continue to use more water. It has a more robust root system. You've already blown through a bunch of water. It's going to use more water here in the green up. So if we're dry through March and into early April, that wheat's going to get more stressed, and we could throw off some of our secondary tillers more easily. So I'm not saying there isn't any wheat out there that has significant damage at this point. I think there could be, but I do think the bigger issue right now is just that wheat that's overly growthy, particularly if we happen to be in a spot where we haven't gotten as much moisture. I think that's probably the bigger risk right now is just the water use and that we burned through some water that we didn't really need to burn through in terms of producing yield. I think the biggest risk still is the crop development being ahead of schedule. And really, whether we're ahead or behind normal curve in crop development almost always comes down to February. If we have a pretty cold February, we're going to probably push our heading dates a little bit later. And but if we have a warm February, we're going to push our heading dates a little bit earlier. And so I think with the February that we have had, I very much anticipate, depending on what we get from here on out, but we're on track for a crop that's ahead of schedule significantly. So I would not be surprised to see us have some heading dates in later part of April, particularly in South Central Kansas. As you go north, yeah, that's going to get pushed a little bit later, but kind of being pushed a couple of weeks ahead, up to 2 weeks ahead of normal is kind of where I would almost expect us to be. And so while I am worried about whether we got a really cold event over the next 3 weeks, I'm probably still more worried about what happens in mid to late April when that plant is moving toward heading and flowering. we're going to sweat out every cold front that comes through in the latter part of April and the first part of May. A Mother's Day freeze this year would be very disastrous. Probably something even in the latter part of April is going to be a big problem for us, just because I think that crop is pushed to an earlier maturity. So, kind of my conclusions: wheat developmental patterns are the result of interaction between vernalization, photoperiod, and temperature signals. Every variety is going to behave a little bit differently. Saturation of vernalization requirement does not equal loss of cold tolerance. So, just because everything's vernalized doesn't mean we've lost our cold tolerance. But as we begin to lose that cold tolerance in the spring, as temperatures warm up and that plant starts to turn reproductive, we do lose our cold tolerance fairly quickly, and that's only partially reversible if we get a period of cooler weather. And finally, ugly wheat doesn't equal dead or damaged wheat. So it may not be very aesthetically pleasing out there in the field, but that doesn't mean that we've lost yield. I'll go back to a few years ago when we had some winter Durhams out in out by Goodland, and I think our grower was like, "It's gone, it's dead. I need to take it out." I'm like, "No, no, 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 no. Just a little bit of patience." We ended up getting hammered by fusarium at the end of the season, but if we wouldn't have had the fusarium, we probably would have had 85, 90 bushel wheat out of that. So it can look really bad right now. It's really that growing point that matters. Um, so that was kind of the vernalization, cold, growthy wheat piece of it. So if we want to kind of pause here and see if there's questions.
So, guys, if you have questions on what the wheat's looking like in the field, go ahead and put that in the Q&A box. I'm going to go ahead and start us off with a quick question, Alan. As we are out looking at wheat right now, it feels like that upper 3 inches or so is kind of dry based on the fact that we've had a fair amount of growth and not a lot of help from Mother Nature in some spots. So, does the cold and the soil being drier open us up for more concerns about a cold snap?
Yeah, I mean, because that plant's already drought stressed. There's actually a couple of things that work in opposite directions. And so you're already stressed, but then also you also get an acclimation to those drier conditions. So that plant, depending on the variety, it can produce small molecules in response to that drought stress. Those are also cryoprotective. And so sometimes those molecular mechanisms of cold tolerance and drought tolerance look really similar. And so you might get some induction of things that might tolerate that a little bit better. Um, but yeah, it is a little bit of a threat. I think the bigger threat from the dry is just particularly with growthy wheat. That plant's going to sense that, and it's going to start losing tillers. And so any of those follow tillers that you built, the wheat plant's pretty good about going, nope, I got too many tillers. I can't carry this. I don't have the conditions to do it, so I'm going to slough those off. So as soon as you start to lose those tillers, that you're losing yield potential. Um, Most of the time that's okay because it's just adjusting to the environment that it has. And if it were to try to carry all those tillers, you'd get low test weight. You'd have issues with that. But I think it's probably more loss of tillers that I'd be concerned about than anything else right now.
Sounds good. Thanks, Alan. Anybody, or let's see, Helen or Aaron, are there any questions either on YouTube or here on Zoom?
I don't have any on Zoom.
Okay.
All
All
right.
right. Well, I suppose, Alan, why don't we go ahead and switch gears and talk about what you guys are working on for going after wheat streak mosaic virus or all the other viruses. Sorry, I kind of clump them all together, and I know we're supposed to separate them out.
Well, you actually hit my first point that it's actually a complex of viruses. We do tend to just call it wheat streak. That's both fine because it's shorthand and they all look very much alike. I don't know of anybody who can accurately go into a field and go, that's wheat streak and that's trimvy and that's high plains. You really need the diagnostics to be able to separate them. But we do have multiple viruses out there, and wheat streak's usually the big one. It's usually the one that's present at the highest frequency. But we also have triticum mosaic, and I would say it's been increasing in frequency the last few years. We're really kind of seeing more and more triticum mosaic. The other thing that's a little bit different is I would say 5 years ago, I would have told you we're very unlikely to see triticum mosaic in the absence of wheat streak mosaic. So we would be saying that kind of we not need to have wheat streak in order for triticum to really infect. And once we have that double infection, then it's really, really damaging. Those plants pretty much just die. I think Lucas Haig had a picture last year of a field of monument that looked like it had been sprayed with Roundup. It was really just an infection of both wheat streak and trim V. And so but I would say in the last 3 or 4 years, we've started to pick up a lot more instances where it's just triticum mosaic. And I don't know whether that's changes in triticum mosaic, if that's some differences in varieties. We do know that there are some genetics out there that are more susceptible to triticum mosaic alone. So we do see that. I don't. So it's a little hard to separate that out, but it is something that concerns me is the amount of triticum mosaic that we're seeing. High Plains is still out there. It showed up a fair bit last year. It's less frequent than the other two, but it's still around. And all three are vectored by the wheat curl mite. So same vector is going to transmit them all. So here's our second question is normally when we talk about wheat streak, we're kind of past the point where a lot of our management tools are gone because our primary management tool is how did you control volunteer? So how well do you think volunteer wheat was controlled in your area this last fall? Poorly, fair, good, or excellent? Uh, because this is the one we've kind of been hammering on is what we can do the best to reduce our risk is to control our volunteer.
Okay, we've got the poll up and the poll's running here. Um, we'll give you guys just a few more seconds. I know we launched the wheat-free period this last year with our extension efforts. So a month ahead of recommended first planting date, we talked about keeping volunteer wheat controlled, dead, dry during that month period, which was a change from what we've done in the past, which was a 2-week period of dead, dry volunteer. So that was kind of launched this year. So I don't know if you guys heard about that in your area, but that's kind of our answer. Feels like an ounce of prevention is worth a pound of cure on mosaic viruses. So. Okay, we've got almost everybody in participating on that. So let me end the poll here and we will share the results. Okay, so it looks like 9% said poorly controlled, 41 fair control, and 45 good control. We had 5%, one person said they had excellent control. So that is good.
Yeah.
Well, good that we have one with excellent control, not great that we've got several or a few with poor control.
Yeah. And I think probably my concern, really across the state, it probably less in the area where I think most of your folks are from, but last year we had that 4 or 5 day period of like 50-mile-an-hour winds that we never got to nighttime temperatures below a dew point. And so it was basically just a high-speed dryer, and we shattered wheat all over, which ended up being basically the same as having nearly a statewide hailstorm. And then we also had a lot of rain during harvest and ended up with more wheat on the ground. So we were really set up for an issue. And I'm still really concerned about this growing season and what we're going to see in terms of our wheat streak. So in terms of the genes that we have available to us, the first one is WSM1. This gene's been around since the 1980s. It comes from a wheatgrass introgression, Thinopyrum. And it's been around since the 1980s. So the first question might be, okay, if it's been around since the 1980s, why don't we have this in our crop? The big reason is that for the most part, it was associated with yield drag. So this is a species very different than wheat. We can bring genetics from Thinopyrum into wheat, but those chromosome segments don't recombine with wheat. So we tend to get a really big chunk of DNA from Thinopyrum. And so we had the gene for wheat streak resistance, but we also had a whole bunch of other genes on that segment, and those were negative for yield. So we would see 15-ish% loss of yield in situations where we didn't have wheat streak. So very protective against wheat streak. But if you didn't have wheat streak, you were giving up a bunch of bushels. So the Wheat Genetics Resource Center did some work on chromosome engineering. There's some tricks that we can employ to induce recombination between wheat and that piece of DNA from thinopyrum. And the Wheat Genetics Resource Center produced a shortened segment that we call REC 213. It just stands for recombinant 213. So it just means that was the 213th plant that we looked at that they looked at that had a recombination event. Um, so it's a much shorter piece of DNA from thinopyrum. Mary Gutierrez initiated a project to look at this and ask, okay, what's the effect on yield now? Her data would suggest that we no longer have a yield deficit for having WSM1. So it looks like this is a gene that we can use. There's maybe a slight negative effect on quality, but it's not huge. It's something that we can deal with. And so it looks like we can use that shortened segment to break linkage drag. Mary released a variety called Burned. It's out of the USDA program here. It's going to be released through Colorado State. This is a line that carries WSM1. It also carries the curl mite gene. So I would say it's a pretty competitive variety from an agronomic standpoint, but maybe not at the very, very top end of the yield potential list. So it's one where I would say if you suspect you're going to be in a wheat streak area, particularly in the western third of the state, might be one you want to think about. The advantage here is that it gives you protection against wheat streak and trimvy. So we do get protection pretty much against the whole complex. So Mary's run a wheat streak trial in Lane County out west of Dighton for a number of years. And that tends to be a mixture of viruses. So it's a cornucopia of viruses. It's not just wheat streak. This thing stands out like a beacon in the field. It doesn't look like it's really hurt at all. We're moving some of this resistance. We've had some of that stuff out at Dighton. Looks really, really good. So I think this is a really good tool for us going forward. It is reported as being temperature sensitivity, having some temperature sensitivity. So at higher temperatures, that resistance can break down. The problem I have with a lot of that temperature sensitivity stuff is all that's done in a growth chamber at a constant temperature of either 18 or 21 or 22 degrees C. And obviously, we don't have constant temperatures in the field. And so I'm not saying there aren't situations where we could have loss of resistance due to higher temperature. I just don't see it very often. I don't think I've seen a lot of instances where I'm like, oh man, I think we cooked that resistance by getting too hot. So I think this will be a really nice tool for us going forward. WSM2 is a gene that we've had for quite a while. It was found first in the Colorado experimental line. It's a wheat source, so there's not the issues with yield drag because we don't have any DNA from a different species floating around. And this one's the one that's been widely deployed. So Joe, KS Territory, KS Tradition, KS Mako, KS Dallas, Guardian, a number of different varieties have WSM2. This is also temperature sensitive, so we can see that loss of resistance at higher temperatures. I'd make the same comment I made under WSM1. That's all done under constant temperature. There might be specific instances where we erode that resistance because of high temperature, but I don't think it happens very often. So this gene's given us pretty good protection from wheat streak, but invariably on something like Joe, we'll get calls about, my Joe's got wheat streak. Well, it probably doesn't really have wheat streak, but it almost certainly has trimvy. And so the problem with WSM2 is it gives us absolutely nothing to trimvy. I think Eston Mason would even say he thinks maybe WSM2 things are a little bit more susceptible to trimvy. I don't know if I agree with that. I don't know that we've really shown that, but we certainly don't get any benefit out of that. So even in central Kansas, we've started to pick up more mixed infections, but certainly out west, in the western half of the state, we've seen a lot of mixed infections. And so the WSM2 is helpful, but it really can not have a good outcome. We've seen that on the WSM2 materials. Like, yeah, if we just have wheat streak, that's great. It's pretty protective in those situations. But if we have a mixed virus infection, you still are very vulnerable with WSM2. The third one is WSM3. It's similar to WSM1 in that it's derived from thinopyrum. It's a different gene. It has the same sort of yield issues. It was shortened once. That shortened line was looked at by Mary Gutierrez. and I think I might have it on the next slide. If I don't, I'll talk about it when I flip the slide. It does give us good protection against weak streak and trimby, and it's a little bit less temperature sensitive. Again, I think the difference in temperature sensitivity in most environments, in most locations, in most years probably doesn't really matter very much. But it does have a little bit less temperature sensitivity. CSU has released a variety called Gabriel that carries WSM3. There's an advanced line in Gorong's program that also carries WSM3. And I guess I didn't put so the problem that we have with this is Mary Gutierrez's work this past year. She had material out in the field that allows us to really kind of parse out what's the effect of WSM3 on yield. So when we had virus pressure, the WSM3 material and the non-WSM3 material yielded about the same, although the WSM3 material had a little higher test weight. That's kind of a red flag because under virus, you would expect better performance, not equal performance. When those materials were looked at in the absence of virus, there was between 13 and 25% yield loss for those things that carry WSM3 compared to those that do not. So I think the conclusion out of this is maybe there's some background effect in the degree of yield loss to WSM3, but this is a gene that's probably not quite ready for prime time. Again, it'll be, if you're going to have wheat streak, maybe it gives you some protection, but in the majority of cases where you don't have wheat streak, you're going to have a yield deficit to it. The Wheat Genetics Resource Center has two segments that are shortened further. And so I'll talk a little bit about that in sort of our strategy here. So hopefully those have less yield drag and we can start to use WSM3. The other piece is that we do have some tolerance to wheat streak mosaic virus. This is just a picture from Belleville in 2024. Pulled up to the nursery and went, uh-oh. I don't like all that yellow, but this was pretty much just wheat streak. And so we were able to do some mapping on this. And so there were a couple of regions that we found. The one on 3B is probably WSM2, but the one on 7B, it would appear to be a tolerance gene. So this would be things, probably what's present in things like Jagger and Overly and WB4458, and those things that just seem to hold on better as opposed to things that are just flaming susceptible, like a Bob Dole or a Hatchet's awfully susceptible. Those things probably don't have that tolerance. So this is valuable in that it'd be really nice to put this in the back, make sure we keep this in the background of our varieties. So if we have a resistance gene and it breaks down, that we don't go from resistant to flaming susceptible. But this is probably not a source of resistance that's enough on its own. But it does appear to be pretty simply inherited. That's positive in terms of using it in the breeding program. We've seen some variation in temperature tolerance of WSM2 material, particularly out of Gorong's program. Could it be that things that also have the tolerance gene show a little bit better tolerance to wheat streak under higher temperature? Does it influence the triticum mosaic virus response? We don't know that, so we're working on developing some materials to ask that and then get to the mechanism to see whether we can use that. I think the tolerance is nice to have, but it's not a silver bullet. It's not something that's terribly protective for our growers. The other gene that we're using some is the curl mite resistance gene. This comes from a wild wheat relative, but it does recombine freely in wheat. Really first came into our germplasm through TAM112, then into bird, Avery, Langan, Guardian. So a lot of the Colorado material has CMC4. So this is resistance to the wheat curl mite. It's helpful, but it's not a silver bullet. So if you plant a curl mite resistant variety, mites blow into your field, they're still going to feed and transmit the virus. What it will do is just prevent that from marching across the field. So you'll still see damage on the edge, but hopefully it doesn't just take over the whole field as those mites end up dying off before they can reproduce and move into other areas of the field. A little bit of a concern. We've had mite resistance before. TAM107 was released in part because of curl mite resistance, no longer effective. Gary Hine at Nebraska has shown that rearing mites on plants with the CMC4 gene for multiple generations results in less efficacy of that resistance. And so if we keep pushing this curl mite resistant button, our curl mites are going to not care pretty soon. They're going to go, we're fine. We can overcome that. So this is kind of a complementary approach to resistance, but it's not a silver bullet. So we need to kind of be a little bit careful how we deploy these things. Just to talk a little bit about what we're doing in terms of breeding approaches, the Hayes program has WSM2 at a high frequency. The vast majority of lines that come out of Gorong's program have WSM2. Some lines with WSM2 appear to have a little bit better tolerance to triticum mosaic. I would say that's more of a degrees of separation than really a completely resistant sort of response to triticum mosaic, but there are some things that look better. Gorong does have some WSM1, and as I mentioned, he has a WSM3 line that he has in advanced testing right now. But again, that gene was associated with yield drag in the Gutierrez trials. So I suspect that if it gets released, it's probably going to be an emergency use rather than for situations where wheat streak is expected, rather than something that you would plant no matter what. In the Manhattan program, we have not used WSM2 as much. I've tried to incorporate it. We have it in KS Mako and in KS 15016717, which is a line we expect to release this July. So we do have some of that protection, but again, it doesn't really give us much for trim V. Our focus has been on increasing the frequency of WSM1 through back crossing. And we also are using that shorter translocation with WSM3. There's no guarantee the yield drag issue has been resolved, but it's more likely that it's resolved in that than the one we know where there's yield drag. So we're kind of taking an all of the above approach. We're also using CMC4. And we do have that background tolerance in quite a bit of our material. So really kind of trying to use all of those things. As far as how we're approaching it as a strategy, we're in the process of building what we call a universal donor. And it has these sets of genes. So for leaf rust, it has 4 genes. For stripe rust, it has 4 genes. For soil borne, it has a gene for acid soil tolerance, has a bunch of genes for stem rust. And actually the WSM1 segment gives us really strong resistance to stem rust, including the UG99 races in Africa. FHB, Hessian fly, curl mite, WSMV, and quality. And so we're back crossing all of these into a provenance background. And the idea is that when a line enters the advanced trial, we'll cross onto the universal donor and we'll ask, what are the 3 genes that this line would most benefit from having that it doesn't already have? And so that we can take away some of the things that are risk factors for our producer. And I think if we do that systematically, we can either release it at the same time as the main background, in which case we'd probably just release it instead of the primary background, or maybe we're only a year or 2 behind with something that has a better package in terms of disease protection or quality or whatever we need to fix. So right now we're running a conversion program. We started with Burned, which is the line that I talked about from Mary's program with WSM1 and CMC4. We now have that WSM1 and CMC4 back crossed fully into Providence. So we're using that as our source more frequently. The value here is the conversion approach provides potential commercial varieties. So we're putting these into backgrounds we already know succeed. So producers know, hey, we're getting something that we know and is going to perform on our farm. The other thing it does for the breeding program is it gives us some really good parents that we know perform as parents in the breeding program well, so that we can really push the resistance throughout the breeding program quickly, because that's always a challenge is we've got a gene, but if it's in very, very few lines, then it's as parents, it's also going to be present in very, very few lines that we release. We also have some materials that are going to be useful for virus research. So the Providence series, we have Providence plus WSM1 plus CMC4. There's 196 rows of this on increase in Arizona. We should get back around 5 bushels of seed. That will go for increase for potential release. I could maybe get pushed out in 27, but probably in 2028 as a potential variety release. But we also have Providence plus WSM1, Providence plus CMC4, and then of course we have Providence. We also have a Providence almost done with WSM2. So from a research side, we can ask questions these could go out as sentinel plots everywhere, and we can ask, okay, is WSM1 responding the way we expect it to? Is WSM2 responding the way we expect it to? We can evaluate some of that from a virology standpoint. And so that's a research tool. This is the work that we're doing in the conversion program. So I have KS Mako with YR5 and 15 for stripe rust. It already carries WSM2. This summer, we'll complete back crossing of WSM1 and CMC4 into it. So it will have WSM1, CMC4, and WSM2, which right now, I don't know how to give you a better package for virus than that. KS Bill Snyder will finish back crossing this summer, adding in WSM1, CMC4, and also the soil-borne resistance gene that I think it has some tolerance or resistance to soil-borne, but it's not as strong as it could be. So we're fixing that as well while we're doing that. So again, those would be things we can start to blow up and move toward a release of something that has a stronger package for wheat streak. The line we're going to release this July. Later this fall, we should have WSM1 fully back crossed into it. We released KS Chicaskia last fall provisionally. It has a high fiber trait to it that we're trying to capture maybe in an IP market. We'll have that fully back crossed by fall of 27. KS Flintlock will have fully back crossed by spring of 27. And then Tradition, we're just starting, but spring of 28, we should have that fully back crossed. The KS20 0463 S4 has done really well in the breeding program the last couple of years. It's a fairly late maturing line, but we would have that completed in spring of 27, moving WSM1 into that. And then the rest of these lines are all lines from either my program or Gorong's program that are in the advanced stage of testing. And so we're not going to complete all of these, but we're going to go, okay, which ones of these do we actually move forward for potential variety releases? And we'll complete the back crossing in that. So we can deliver varieties that have all the good characteristics of the background variety, but also have the wheat streak package into it. I think that gets us to a high level of resistance that gives us protection to wheat streak and trim V quickly and does not sacrifice yield in environments where we don't have wheat streak. And so that's our approach to breeding right now. I'm pretty happy with where we're at. I think we're at the point where we can start to push things through pretty quickly, and the gap between releasing the base variety and the variety with the improved wheat streak package is not going to be very long. And so we'll have tools that I think we can push out to producers quickly that are going to do really well in their field and give us protection. Once we have these, I would say does not mean we should skip our management practices. It's going to be really important that we continue to do the right thing, or we will risk losing these disease resistance genes. We do have the shortest WSM3 lines, and we've started crossing those to Mako, Providence, Tradition, and then a set of other lines. We'll expand that a little bit, but we'll push that WSM3. This will allow us to evaluate the yield effect of WSM3 as well. And if it doesn't have a yield drag, then great, we've got adapted material that's ready to roll into producer fields. So I think that's the end of what I had on viruses. So be happy to take any questions.